So, okay guys, in the previous class I taught you if your system has non-zero set point that you want to follow, like a 75 degree of 75 Fahrenheit of the temperature of the room, or if you use the speed of 65 mile per hour in the highway, that you want to use a cruise system, and your system has integrator. So like this example that we had in the previous class in MATLAB, that's right, and I gave you how to design the controller analytically. Remember, this was the previous class, that's right. 1 over s plus 1 in s plus 2 was s plus 3, that's right. And now, and this is feedback, unity feedback. So we have non-zero set point that you want to follow. This is that you want to, the desirable input that you want to follow, and this is the output of the system, that's right. And you see that the open loop transfer function here has integrator, because I told you from undergraduate control the Laplace of integration is 1 over s. This is undergraduate control, that's right. So, and you know that from the PID controller from undergraduate, refreshing your mind, I controller, this is I controller, removes, as I told in the previous class, the steady state error signal, or the function of I is that make error signal to 0. What is error signal? Here we go, that's right. Here error signal is what? R minus y. That's right. The real output of the system. This is the real output of the system. Real time, real output of the system. And it's a desirable input that you want to follow. Desirable input. So in the previous class, as you saw, we designed the controller. This is U, I'm saying U. U was, as you saw, was minus kx, gain that we use the Ackermann formula in MATLAB, plus k1, k1 in R. K1 is the first element of this, first element of the K. As you look at part 14 in the YouTube, you can see it. And then if you remember from previous class, if you want to follow 75 step function, means here was 75, remember, and after that, implementing this controller, it becomes like this. That's right. So now let me try another example. The example is this, guys, with you, because I'm gonna teach you another controller, plus minus R, the same R, and suppose you have, this time you have this one, s plus 2 in s plus 3. This is a second order system. There's a similarity between this example and this example. So what's the similarity? I already removed the I controller here, that's right. There is no I controller. So this problem says I want to follow step function or non-zero desirable input, but system has no integrator in the open loop transfer function. System has no integrator. So having this, I want to again examine this. So so I'm gonna again use this minus kx plus k1r. So first, let me denote the state space. Look at here, guys. If I go to the next page, so look at here, guys. So this is y. This is, suppose, u. Sorry, this is u come from the controller. So y over u is 1 over s plus 2 in s plus 3. Again, we remove the integrator, and now this is an example. right? So obviously this is y over u is 1 over, then we will go to MATLAB. S squared plus 5s plus 6. So you got s squared y plus 5sy plus 6y is equal to u. Now what we're going to do, I'm going to do the inverse Laplace by saying that assumption is that y of 0 at time 0 and y dot of 0 is 0 initial conditions. You know that from the undergraduate control in the time domain, this gives you the y double dot, right? Plus this gives you 5y dot plus 6y is u. So now go to state space, analytically you say x1 is y, x2 is y dot. Having the time derivative from the both sides, what you get is this: x dot 1 is equal to y dot is x2, right? X dot 2, because we're going to transfer this to MATLAB, is y double dot, but from here y double dot can be found, is u minus 5 y dot is x2, x2 minus 6 and y is x1. So the state space equation by removing the integrator gonna be this: x dot 1, x2, x dot 2 is u minus 5 x2 minus 6 x1. So the difference between this, when you had the integrator, it has 3 state variables, guys, remember? And I'm gonna open it right now in the previous MATLAB code. Right here, by removing the integrator, you have a second order system, so you have 2 state variables, x1 and the x2. But again, here u, I'm gonna use minus kx plus ku1r. This controller, if you remember from the previous class, was for the system that has integrator, right? Now I'm gonna try it for a system that has no integrator. Let me see what happens, huh? So here we go. Let me go to the MATLAB. Okay, so now if I open this from M696, here we go. What happened? Did nothing, M696? Everything has been deleted? What are these guys? Oh, we do have it. Yeah, here we go. So if I open it, the previous class was Ackermann third, that's right, if you remember. Yeah, this was the system, was third order system in the previous class, part 14 in the MATLAB. So I'm gonna just copy and paste, because I'm gonna, if you have a second order system, I want to say with that, I say Ackermann third, this is second order system. I'm gonna write here, please do it at home with me, this system has no integrator. We want to examine that, okay? So now if I want to save it, it's gonna be again MS696 second order system. Well, it must be the same name. And you have 2 state variables, it's gonna be 2. And now your look at here. Let me do it here. So if I want, so if you write and the state space, it's gonna be like this: x dot 1, like this, x dot 2, x dot 1, x dot 2, based on from here, gonna be, see, x1, x2. In the first line there's no x1, so it's 0 on 1. Second line gonna be -6 and the -5 plus bu, single input, single output. So this is gonna be scalar. First line there's no u, 0. Second line gonna be 1. So this is your a and this is your b. For what? For finding what? For finding the gain matrix again by using Ackermann methodology. That's right. But let me double check everything because I'm human, I can make mistake. 6, so this is gonna be 5, and this is gonna be 5x to 6x1. Okay, so this is your a, this is your b. So now if you look at here, I'm gonna keep the dominant complex conjugate poles as a pair of complex conjugate poles, like as the previous case. But here you have to have two because your system is second order system. So I keep it as a pair of complex conjugate poles to yield. Suppose your system wants you that you have an underdamped system to yield underdamped transient response. Please do it at home with me, practice, okay? Now we can have this. So I'm gonna keep it as first for 1, and here you're gonna have, because you have this, it's gonna be again 1 and 1. Takes 1, so we don't have, you have two state variables. Here we go. Here's gonna be, let me see, -5x2 and 6x1, right? 6x1 minus 5x2. Here we go. Right? Now we have our second order system. That's right. And now from the previous class, Ackermann solver was this, right? I'm gonna make it another file because I don't want to combine them. So here are gonna be second order system. I'm gonna call them second, remember? And because I have to save it as Acc second solver, where at ME696. I saved it. So I have two state variables. So because I made this assumption of initial conditions are 0, I made this assumption here. So I'm gonna do that here at the same time. Now, so and now here we go. And this is the first element of. This is say now here is a unit step. So let me see. Hopefully, O and your B must be second order as we did. Oh, I didn't modify this. Oops. Sorry, guys. So your system, your A is this. Look at here, guys. 0, 1 minus 6 minus 5. For by removing the integrator, you have 0, 1 minus 5, and B is 0 and 1. That's right. Look at here, B is 0 and 1. Here we go. This is 0 and 1, and this is 0, 1 minus 6 minus 5. Here we go. So now we have second order system by removing the integrator, okay, from the system. So if I run this, let me first debug it. Change folder. So there's some typo. Let me see. Oh, I remained as RD. Must be but second. It doesn't matter. So you see, guys, this time you wanted to go, guys, you wanted to go to 1, but your system ends up to what? To almost 0.15. You have a huge gap, you have an error, because I intentionally removed the integrator from the system. So this formulation for the error signal, this formulation is only valid when you have an integrator in the open loop transfer function. Okay, you have to have integrator. So when you don't have and try to trick the MATLAB, you're gonna say, hey, I'm smart. Understand? So you see that we have to go to 1, but we are stuck at 0.15. Understand? Your system is under damped, as you see, but you have an error signal. So on the other hand, if you wanna see, let me say, is E as error signal is R minus x1. R minus x1, right? Now if I say figure 2, say plot time and E, and it's gonna be blue and dot here, and hold on, let us see how it looks like the error signal. So error signal is gonna look like this. Right, it's gonna be error signal. Error signal gonna be how much? This value, right? 0.5. The error signal value gonna be how much? Almost 0.85. Almost 0.85, as expected. That's right. So because why? Because we removed the integrator from the system. So what's the solution of that? We have to have some solution for that. So I'm going to do that for you today. So now that's why we go to the next topic in the design and control. Solution is this. Recording this. Solution is, for God's sake, is this. We say, okay. Design of type 1 servo system when the plant or your system I'm changing the color, has no integrator, has no integrator, and desirable input or reference input is again non-zero. You want to track the 75 Fahrenheit of the room, temperature of the room is again non-zero. Here we go. Okay, so what's that? The solution is this. This is how we design controller this time. If the system has no integrator, we insert an integrator, integrator in the feed forward path between the error and the plant. Here we go. How we do that? Look at here, guys. This is non-zero reference input. This comes here, plus minus. We're gonna add integrator. This gonna be zeta dot. Bear with me first. I'm plotting. See, I'm adding an integrator. Okay, integrator to the system. If you integrate from zeta dot, this is kindergarten mathematics. This is gonna give you zeta, right? Then I'm gonna multiply this by ki. I'm gonna talk about the ki, and this goes to another things, plus minus. This gives you control input that I'm gonna design based on these parameters, and this bu, as you know, in bu, this gonna be adds up to another ax, that's right, plus this gonna be some this gonna be x. In x, one branch comes multiplied by ax. This adds up to this ax plus bu gonna be x dot. So here is x dot. Remember, this is the LTI system. So x dot is equal to ax plus bu. Then this gonna be multiplied by c matrix or vector, gonna be output y is equal to cx. Then this x gonna be multiplied by matrix gain. Now this comes here, subtracted from this part. This is minus and this is plus. Let me rewrite it. See, this is minus, here is plus. Then output gonna be subtracted from the input to give you this. This is how we design the controller. So let me go one by one mathematically. Then we will go to MATLAB. See, obviously we are working on LTI system. X dot is equal to ax plus bu, for which case when the reference input is not 0 and there is no integrator in the open loop transfer function. Integrator, look at the example that we just developed in MATLAB, right? And we know that y is equal to cx. Now if you look at this block, u is equal to, guys, minus kx, state feedback control law, as I taught you several times in this course, minus kx plus ki in zeta. Look at here, ki in zeta. So now we are using this controller, guys. We just modified controller. Minus kx, as you know it, this is state feedback control law, plus ki in zeta. So, but zeta is the operation of integration, that's right. You see, so zeta is what? So sorry. So zeta dot, because zeta dot is r minus y. That's right. So zeta dot is r minus y. What y is what? We know from LTI system is cx. So it is r minus cx. Here we go. This is novelty of this controller. Understand? Okay. So hold on, I want to decide about this. Okay, now this is mathematics part of that. Bear with me, guys. Okay. So you have to know it's mathematics. So now look at these guys. Based on these equations, okay, so we have two state equations. One of them is x dot is equal to ax plus bu. Another that we just generated was this zeta dot is equal to r minus cx. Or you can write like this, minus cx plus r. Yes or no? Okay, now we can write these equations in the matrix format. You can say x dot zeta dot is equal to, look at here, guys, you have x, that's right, and you have x also here, but you have no zeta. So here is x and zeta. So here you have axa. Do you have any zeta? No. So it's gonna be 0. Here again you have x, so it's gonna be minus c. Do you have any zeta? No, 0. Plus, now let's talk about u. Single input, single output. So this is gonna be, here first line gonna be only b. So it's gonna be b. Second line, there's no x, there's no u. Gonna be this. Plus, what about the input? Because we have r reference input. In the first line, 0. Second line, yes, r of t. That's right. So we are now changing by adding integrator for the system that wants to follow non-zero reference input. We are adding another virtual state variable. This is another virtual state variable. So what we're gonna do, we need to design asymptotically stable system. I taught you about very short about asymptotic and Newton stability, in which x at the steady state value at time infinity, zeta at time infinity is steady value, and u at time infinity steady state value tend to constant values. But the question is why they have to tend to constant values, guys. Zeta dot, if zeta, guys, at time infinity becomes a constant value like n constant value, so what gonna happen for zeta dot? So zeta dot at time infinity, how much gonna be from high school mathematics? Gonna be 0. What is zeta dot? It is r minus y. Get here, gonna be 0. So output finally gonna go to desirable input. Understand? So that's why we want to have that the state value of x and zeta and u tend to this. But we have a little mathematics we have to do with this, okay? Before going to the math lab, we have to understand the background of this first. So now, based on whatever I wrote, you're gonna say x dot at time infinity and zeta dot at time infinity gonna be from using this, guys, using this relation, okay, gonna be again a0 minus c0. Now again, x at time infinity, zeta as time infinity, steady state values, plus b0 u at time infinity plus 0 and 1, and this is r at time infinity. That's right. If for example your r is unit step, so r at time infinity gonna be again r. That's right. So by having that, now I'm naming equation 2 and I'm naming this as equation 1. I'm gonna subtract 2 from 1. If I do that, you're gonna have this x dot t minus x dot at infinity, z dot t minus z dot at infinity is equal to, again, a, we have to factor out this matrix. Now here, this is 1 minus 2, this equation, x of t minus x at infinity, zeta of t minus zeta at infinity at the state value, plus again b this u of t minus u at infinity, plus, so because this is finally r, so r minus r gonna vanish, so there's no plus anymore. Understand? Huh? Then we redefine the state variable, then defining x dot of t minus x dot at the state value as x dot of et, and then zeta of t minus zeta, let me do not dot because it's gonna be easy for after differentiation, zeta at time infinity as zeta is error signal of x, error signal of zeta of t, and u of t minus u at time infinity is steady value of the control signal, gonna be ue of t. If you implement these inside this equation, simply you get this x dot minus x dot of t minus x dot of infinity gonna be x dot of et, gonna be z dot of et is equal to, again, a0 minus c0 is gonna be x e of t zeta e of t plus b0 u e of t. Bingo. So you see, first take home message is that if you have non-zero reference control, non-zero reference response, and but your system has no integrator, by this kind of design you adding the order of system +1. If your system is second order, your new state variable gonna be third order. If your system is 5 order, your new state variable gonna be 6 order. Okay, This is how we design it. So now for simplicity, I'm naming this as A hat, and I'm naming this as B hat. Okay, so now I'm gonna define. So E of EA, this is the modified control input, gonna be again state feedback control law, but this time this X E of D, okay, this X E of D plus KI zeta E of D. Now you understand why I defined like that. That's right. Now let me define E as, why I define this A hat and B hat. I'm not stupid. E, the error signal, as XE of, because they are different, that's right, at the end. XE of D, zeta E of D. Can I? Yes, I can. I'm gonna implement here. So if I implement here, so you're gonna have E dot is equal to A hat E plus, plus B hat U E. That's right. And this is very famous, that's right. This is very famous because this is very in similarity with X dot is equal to AX plus BU. That's right. But here your state variable now is the error signal. Right? Now I'm not done yet. First you have to do mathematics. Okay. Okay, so we ended up after too many formulations, E dot is equal to A hat E plus B hat U of E. We know that A hat is original A of the system 0 minus C and 0, and B hat is the original B of the system and this. Now you are a control engineer, as I taught you. I'm gonna say, you know what? I'm gonna select the control input of system minus K hat E. I'm just implementing here. So what you get is E dot is equal to A hat E minus B hat K hat E. This is gonna be A hat minus B hat K hat E. Now we know this equation. Remember? I taught you. So what is K hat? K hat gonna be original K that you designed by the Ackermann and Ki. So your new state is the error signal. Understand? So here we go. Right? So in the next class I'm gonna, now because I have to do too many things, I'm gonna redesign this problem guys, by this control signal, and another problem I'm gonna do it the next class is, suppose you have a pendulum, inverted pendulum, and I'm gonna make it upward. I'm gonna do this. I'm gonna design a controller tau or u to make this by this kind of, because this system has no integrator in the open loop. I'm gonna explain why. Okay, the next class is gonna be MATLAB of these examples. Understood? So that's it. Let me see.